Good afternoon, everyone. We will start the second session in the third day of the APCTP Winter School. The second session. In the second session, Professor Dong-han Yeom will teach the geometry of evaporating black holes. Let's welcome him.
Okay, thank you very much. In the first day and second day, I have discussed about the origin of Hawking radiation. And in addition, yesterday I discussed about the Bekenstein-Hawking entropy. So based on these two lectures, now maybe we can move our interest to the evaporating black holes. So today the task is to see the very details of the geometry of the evaporating black holes. Of course, you briefly know that the black hole emits the Hawking radiation. So initially there was a black hole, and black hole disappears, and the space-time goes to the Minkowski. And that's all. That is the brief outline. And if you know this, then you know the basic causal structure of the evaporating black holes. That's all. However, sometimes you want to know what happens in in terms of details of geometry and metric and so on. Everything must be dynamical. So you may ask what happens for so if you are located nearby the horizon, then what you will feel. So is there any incoming energy flux or outgoing energy flux, or if you include the geometric back reaction, then how the apparent horizon and singularity behaves and so on. So today I would like to study and cover such topics. So today I will talk about first about the horizons. Of course, you know, there are many horizons. So, but how many kinds do you know about horizons? So today, first I must categorize what is the horizons, and the important point is that there are two different kinds. The first one is causal horizons. So causally defined horizon, and the other is the quasi-local horizon. So quasi-local means that locally you can define some horizons. So there are pros and cons, and both concepts are important. And in the static limit, you don't have to distinguish a causal horizon and quasi-local horizon for perfectly static geometries, but in dynamical situations. So if a black hole evaporates, then black hole spacetime is necessarily is necessarily dynamical. Then, in general, causal horizon and quasi-local horizons are distinguishable. They are very different, and this is very important. So quasi-local horizons are very important to draw and decide the generic causal structures of the space-time. I mean, in terms of dynamical and local sense. So first, once I introduce the horizons, then now I will show the principles. So basically, we have to solve the Einstein equations to see the back reactions. But what makes the back reaction to the black hole? So what makes the incoming negative energy flux to explain the evaporating black holes, and then the necessary thing is to include the renormalized energy momentum tensor to the Einstein equations. Then the principle to obtain the renormalized energy momentum tensor is to do the quantum field theory in curved spacetime. Of course, this craft in curved spacetime itself is a very difficult topic, and there are many difficult issues, and many mathematical details are necessary. But today I will just briefly and historically provide some important references and important progresses, and mainly focus on the most simplest case in two-dimensional case. So of course, what you have to do is four-dimensional renormalized energy momentum tensor, but it is very difficult, and for generic dynamical situations, it is almost impossible to compute. So up to my knowledge, the only doable computation, I mean, in terms of numerical computations, the only doable examples are the two-dimensional formula, which is known by Davis-Fulling-Unruh formula. So by using Davis-Fulling-Unruh formula, we can write the complete form of the energy momentum tensor in two-dimensional cases. So using this rigorous and definite energy momentum tensor, you can plug into either two-dimensional case or four-dimensional case. So in the two-dimensional case, if you plug in, then it is very nice and complete application up to the H-bar order. And then it is more complete, but the problem is that you are limited to the two dimensions. However, even in the two dimensions, there are lots of things that we can say. So these topics are, so the famous examples are known by CGHS and RST. So CGHS means 칼난-기딩사-비스트로민저, and RST means Russo-Susskind-Thorasius. So both models are motivated from the string-inspired black holes in two dimensions. However, if you are further interested in the four-dimensional case, then you cannot directly use this 2D formula, but still you can rely on the S-wave approximation. So you only consider the S-wave. Then this can be approximated by two-dimensional result divided by 4 pi r square. So this is a very crude approximation, but still this can include the very essential nature of, I mean, the qualitative nature of the evaporating black holes. So if you apply the S-wave approximation, then you can compute the evaporating black holes even in four-dimensional case. Of course, you cannot solve it by hand. So there's no analytic solution, but you need to strongly rely on the numerical computations. So these are the way to see the very details of the dynamical black holes. And in order to see the details nearby the horizon, you should follow such a very complicated computations. Finally, so based on these semi-classical analysis, there are lots of interesting topics, but finally, I will shortly remark on this question. So this is based on the usual misconception about the black holes. So the question is, will the semi-classical effects prevent the formation of a black hole or not? Because up to now, there are some people who seriously think about this direction. So I will mention about this. So anyway, so let's start from the most fundamental topic. So this is about the horizons. So I bravely provide the subtitle "Everything About Horizons." Of course, in this series lecture, I will only focus on the spherical symmetry case, and I will not go the details of mathematically rigorous presentations, but I will just introduce very intuitive things. So maybe the very good reference is this paper, Ashitaka and Krishnan in 2004. So this is a review paper of classical and quantum gravity. Probably classical and quantum gravity. No. Maybe the journal name is Living Reviews in Relativity, which is a very important review journal in general relativity community. And this topic was summarized by Ashitaka and Krishnan. And also one very important author in this field is Sean Hayward. He introduced the trapping horizon concept. Anyway, in this paper, they are talking about isolated and dynamical horizons and their applications. So they are saying about isolated and dynamical horizons. So what is dynamical horizon and what is isolated horizon, whatever it is. So there are many, in the market, there are many kinds of horizons. So can you distinguish what is what? So first one is event horizon, second one is Cauchy horizon and cosmological horizon, and operant horizon, isolated horizon, trapping horizon, trapped surface, and maybe I omitted some other horizons. For example, dynamical horizons or whatever. So and also in my previous paper we introduced some other notions. For example, I forgot the even I forgot the name. Maybe maybe adiabatic horizon. Maybe I introduced such a we introduced some new notion of the horizon. So can you distinguish what is what?
Are they all physical? Like, for example, something is like some invariant on the diffeomorphism, or
I think so. I think so. So I think in general relativistic sense, all horizons are well defined. So in that sense, there must be no problem to decide the horizon. But the important point is that
well-defined is okay, but it's whether it's a physical, it might be some different problem, isn't it? Or
that's a very important and good question. That is the point that I will show. I mean, you can define any place as a horizon and by a very reasonable way, but the question is whether it's a physical or not. And then by asking the physicality, so what's the meaning? You may think about this. And the physicality means that can you decide the horizon using the local quantities or not? Because general relativity is Riemannian geometry. So Riemannian geometry means nothing but using the local quantities, you decide the curvatures and so on, everything, geodesics and so on. So the question is whether the horizon can be explained by such a local curvatures or geometry or whatever it is, whether it is defined or not. That is probably the question about the physicality. So the first three horizons are globally defined horizons. So historically, event horizon, Cauchy horizon, cosmological horizons are first developed, first introduced by mathematicians, including maybe I'm not sure, but probably due to thanks to Roger Penrose and Stephen Hawking and the important contributors. So event horizon, Cauchy horizon, cosmological horizons are basically a global concept. So we need to know the entire space-time to decide the horizon. So, for example, we decide the singularity and future infinity, and then there must be some point, crossing point between singularity and future infinity. And from this point, we draw the null direction, null line backward in time. Then this causal boundary is called by the event horizon. So this means that so you, in order to decide here is event horizon or not, you must know the entire structure of the space-time. Even you have to know the future infinity. So if you don't know what happens in future infinity, then you cannot decide where this point is inside the event horizon or not. So in this sense, it's globally defined. Also, in cosmological context, there's a future infinity, space like a future infinity in digital space, and here is R equals 0. There's R equals infinity. Then there is a crossing point here, and from here you can also draw a null line backward in time. This null boundary is called by the cosmological horizon. Again, you can ask whether that point is a real cosmological horizon or not. Then in order to decide this, you must know the future infinity. So whether the space like infinity appears or not. So in this sense, it is also a globally defined concept. Then what is the Cauchy horizon? Cauchy horizon means that, for example, here is space-time. So up to here, you could decide everything. However, at some point, there may appear some time-like singularity. So if it is space-like singularity, then it's okay. But if there is a time-like singularity, then from this point, appears some undecidable region. So, using this data, you can decide this triangular region. However, if there is a time-like singularity, then you cannot decide this point. So if there appears the time-like singularity, then there appears the causal boundary, and beyond the causal boundary, you cannot decide based on the general relativistic equations of motion. So in this sense, this boundary is known by the Cauchy horizon. So of course, the Cauchy horizon is a little bit different from event and cosmological horizon, because you can decide from the past point and you can just draw the null line. However, still it is questionable. So what happens at the Cauchy horizon, and is it really singular, or can you go beyond the Cauchy horizon and we cannot say anything? So the definition of event horizon, Cauchy horizon, cosmological horizon, all of them are defined by the global way. So it's somehow maybe it's a philosophical word, but it's too teleological. So locally you cannot decide them. So as an alternative definition, you may think about more physical definitions of the horizons. So these are locally defined horizons, or somehow you mix the local notion and global notions. So somehow you may say the quasi-locally defined horizons. So then if you define such horizons, then we can know whether this local point is the horizon or not. Therefore, these are some very nice features and more physical concepts. But one negative point of this locally defined horizon is that there are maybe infinitely many ways to define some horizons. So there are many ways to define the notion of horizons, but not all of them are useful. So we need to collect the only useful horizons in terms of Hawking radiation or any other physics. So there are pros and cons. Some globally defined horizons are more mathematically well defined. It's nice. However, these are too teleological. So the quasi-local horizons are more physically defined, but not all of them are useful. So,
why locality important?
You mean why the local horizons are important?
I mean locality, like for example, local like a theory is good, but anyway, maybe classically it's good, but in the end, GR is gauge theory. So I
Yeah.
don't know. I already confused with the physical observable. So in
Okay.
this GR physical observable, there is no local observable.
Okay. So maybe I can change the question. So it is known that around the apparent horizon, I mean the locality. When you say about the Hawking radiation, it's about the particle creation, and then there must appear the trapping region, trapped region. So and then nearby the trapping region, one particle falls in and one particle comes out. Then we need to ask where is such a physical surface where such a trapping happens. However, if the notion of the horizon is global, then locally we cannot decide where this point can, so such a trapping can happen around this region or not. And maybe later I can show some examples that locally defined horizon and globally defined horizons are different, and then we may think some different physical differences between them. Okay, so let me keep going the discussion. So in order to regard the horizon as a physical object or physical quantities, we need to rely on the quasi-local definition of horizons. This is the motivation why we are introducing the quasi-local notion of horizons. So there are many different definitions, but if you are restricted to the spherical symmetry case, then in my understanding, all of the definitions are the same. So this is thanks to the spherical symmetry. For the more complicated situations, then maybe all of the definitions may be a little bit different, but at least in the spherical symmetry case, I think all of the definitions are consistently the same. So for the dynamical cases, I just rely on my review paper about the dynamical black hole simulations. So if you are interested in, then please see this article, and then there are some mathematical details. So, but of course, I will not derive every equations, but I will just briefly show the case of the spherical symmetry. So this is the most generic form of the metric for spherical symmetry. So by generic, what I mean is that if you impose the spherical symmetry, then there are r directions and also time directions. If you ignore the time direction, then it is static solution, but it is not a generic form. So if you include the time dependence with spherical symmetry, then there must be at least two independent functions that describe the spherical symmetric geometry. So this is the generic form of the metric for spherical symmetry, and I use the null coordinates. U is the ingoing null direction, V is outgoing null direction. So this is the double null coordinate, and then alpha is function of U and V, and R is function of U and V. So in the space-time, U is the ingoing null direction, and V is the outgoing null direction. But you can choose this always in any time. So in this spherical symmetry case, the important local quantity to check whether the space-time is trapped or anti-trapped is defined by this one, this quantity. So usually, so in first day, I mentioned that if you decide the ingoing direction and outgoing direction, then usually along the ingoing null direction, the aerial radius should decrease. In the outgoing direction, null direction, aerial radius should increase. By the way, what I have to emphasize is that the aerial radius, R is the aerial radius because R square is proportional to A. It is the local quantities, and in general relativity, you can measure this because it is approximately related to the curvatures. So I mean, I'm saying very heuristic way, but you know, the Gaussian curvature is proportional to 1 over R square, or 1 over R or 1 over R square. That is not very important. But the Gaussian curvature, or its generalization, is the Riemann curvature. So Riemann curvature or Gauss curvature is proportional to the area, is related to the area, and area radius is presented by R. Therefore, R is the locally measurable quantity. So R is the local quantity, and by differentiating this R, if you define the notion of the horizon, then it is very physical, at least in the general relativistic sense. So along the ingoing null direction, usually R decreases, and along the outgoing null direction, usually R increases. But if it changes the sign, so if round R, round V equals 0, then one can say that the space-time is trapped. So, but if something like this. So usually in the beginning, RU is less than 0, and RV is greater than 0. But at some point, you may meet R, V equals 0. This is the horizon, and if you cross the horizon, then you may feel that you are trapped, and your aerial radius decreases whatever the direction, either you go ingoing or outgoing direction. For both directions, your aerial radius decreases. However, it is in principle possible that you cross one horizon more, R, V equals 0 once again, and then you will feel again that your area radius increases along the outgoing direction. So here is r comma v is positive, negative, and positive, and there are two boundaries. Then this case, for this case, if rv equals 0 and rv changes the sign from plus to minus along the outgoing direction, then we can say that it is the trapped. So this is the trapped apparent horizon. I mean, it is trapped. And even though rv is 0, if the sign of rv changes from minus to plus, then we may say it is anti-trapped. So anyway, round v equals 0 is the boundary to distinguish either trapped or anti-trapped surface. Because even an outgoing observer sees the change of decreasing or increasing area radius. So this is physically well defined notion of the cross-local horizons. So this is a very educative to draw the contour lines of constant R hypersurface. So so let me draw as follows. So okay, let me erase it. Oh no. Let's write here. Okay, so. So let's decide this is the ingoing null direction and this is the outgoing null direction. And as I said, no, this is V. And we may think about the constant R contours. And then along the ingoing null direction, R should decrease. And along the outgoing direction, R should increase. So maybe I can draw this way. These are constant R contours, and along the outgoing direction, you can see that R increases. Along the ingoing null direction, R should increase. So if you write down the constant R hypersurfaces this way, then so of course R increases along direction. Then this satisfies R comma U less than 0 and R comma V greater than 0. However, if R comma V goes to 0, then this means that now R should change something like this way. Then along the V direction, R contour lines are somehow R contours are tangent to the V direction. I'm sorry. So, you know, along this line, R contours are tangent to the V direction. And then if you collect all possible RV contours, RV equals 0 contours, then you will see this kind of boundaries. So this is the boundary where RV equals 0. So therefore, you can decide that here is the trapped region. Maybe you can define this red colored region is the inside of the black holes. And you know, if you draw the contour inside the horizon more, then you can draw that. Now constant R contours are now space-like. So you know, constant R contours are time-like in outside the black holes, but inside the black holes, constant R contours are now space-like. So at this boundary point, the R contours are null direction. So it changes from time-like to space-like direction smoothly. So this is the way to draw the R contour lines, and numerically, no, this is a conceptual figure, but you can now understand this way. So these are the R contours, and R increases along this direction. And at this apparent horizon, R changes from time-like to space-like direction. Time-like to space-like and time-like to space-like. So you can understand why this apparent horizon and R constant contours are crossing this way. So mathematically you can understand this, and maybe conceptually and graphically you can see this figure. This is the very essential nature of the apparent horizons. So this is the notion of the apparent horizon, and of course there are several different notions of the quasi-local horizons. But in the spherical symmetry case, I can use apparent horizon or trapping horizon or whatever. So I will only use the apparent horizon for the quasi-local horizons. So now let's see the details of the apparent horizon and from the Einstein equations. So if you plug this metric ansatz to the Einstein equation, then you can write down all the components of the Einstein tensor. So non-trivial components are GUU, GVV, GUV, and G theta theta and G phi phi, but due to the spherical symmetry, G theta theta and phi phi are dependent. So only independent components are these four. And due to the Einstein equation, GUU must equal TUU, TVV, TUV, and T theta theta and so on. So now let's impose the condition for the horizon, apparent horizon. So R comma V equals 0 condition. Then you will simplify the second equation by this form, and the third equation by this form. So I think all the mathematical details are in my previous review paper, and you can easily find many references to write down the equations for the double null coordinates. So that is okay. Then now one more thing is that near the horizon, if you can ignore the vacuum energy contribution, usually the vacuum energy or cosmic constant contribution is related to TUV part. So if you can ignore this part, then this term is approximately negative definite minus alpha square. If one can ignore vacuum energy contribution near the horizon. And then along the V direction, the important thing is TVV. So if TVV is positive, then RV must decrease, because here is a minus sign and here is plus sign. So RVV should be negative, and this means that RV must decreases from plus to minus sign. This means that if TVV is greater than 0, then the horizon must be anti-trapped. Trapped. So trapped region. However, if TVV is less than 0, so if this sign is minus, and then RV should increase from minus to plus sign. And this means that the horizon must be anti-trapped region. And so either the horizon is trapped or anti-trapped is related to the energy momentum tensor at the horizon, and whether its sign is positive or negative. This is a very important signature. And you may ask whether the horizon is space-like or time-like, but it comes from this second equation. So along the U direction, RV always decreases, because if you can ignore TUV term, then you can notice that it is negative definite. So always RV always decreases from plus to minus sign, because it is negative definite. So this, if you please sit down on your desk and draw all possibilities. Then from all of these informations, you can decide that if TVV is greater than 0, then the apparent horizon is space-like. Horizon is space-like. If TVV is less than 0, then the apparent horizon is time-like. This is a very important thing. So if there is no energy momentum tensor, then the apparent horizon is null. So if it is null, then it can be the same as the event horizon for the static case. But in general dynamical case, If TVV is greater than 0, then it's space lag. TVV less than 0, then it's a time lag. Then what is the physical meaning of TVV? TVV means that TVV is the incoming energy flux. So the sign of TVV is related to the so-called null energy condition. If TVV is greater than 0, then null energy condition is satisfied, and there is an incoming energy flux. If TVV is less than 0, then null energy condition is violated, and there is an incoming negative energy flux. So you may interpret that if there is an incoming energy flux, then the apparent horizon is space-like. And if there is an incoming negative energy flux, or equivalently, if there is outgoing positive energy flux due to the evaporation, then the apparent horizon must be time-like. So this is the very fundamental principles to decide the local horizon dynamics in evaporating black holes. So let's see let's apply for the Schwarzschild black hole case. So this is the global structure of the static space-time. And in 2 days ago, I mentioned that we have to cut the star interior as a time-like surface, and cut and paste the star interior and outside the geometry. This is the dynamical formation of a black hole. And then, thanks to Hawking radiation, we can notice that black hole will evaporate, and eventually it will go back to the Minkowski geometry. Therefore, this is the Minkowski space-time, and we cut some part of the Minkowski space-time and identify to this geometry, and we obtain the very famous evaporating black hole structures. Now, from this geometry, we want to decide where is the apparent horizon. And as I mentioned, if there is incoming energy flux, so I mean incoming energy, if incoming energy is dominated, then apparent horizon is space-like. And after the star collapse, now the incoming negative energy flux is dominated. Therefore, this horizon must be time-like, something like this. So this means that this apparent horizon is not the same as the event horizon. So either it is inside the event horizon or outside the event horizon. So for dynamical black holes, a locally defined horizon is more meaningful, and so the very naive approximation to draw the dynamics of the apparent horizon is to use the Vadia-like metric. So this is not the solution, but just an approximate description for the dynamical geometries. So if you use this Vadia metric, then the apparent horizon is located at 2m. And by solving all the equations, so especially in order to draw this equation, I mean, in order to draw this picture, what I assumed is dm dt dv. dm dv is minus alpha 1 over m square. So this is the consistent Hawking like formula. So based on this assumption, you can solve all Vadia-metric dynamics. So the apparent horizon behaves something like this. So from 0 to time 10, apparent horizon grows from 0 to a very big radius. So during this time, apparent horizon grows due to the star collapse. And after this time, Hawking radiation is turned on, and such a evaporating speed increases as time goes on, and eventually disappears at this point. This is the end point. And from this end point of the evaporation, you should draw the null direction backward in time. So backward in time, you draw this null line backward in time, following the Vadia metric, and then this blue curve becomes the event horizon. So this is a numerical computation based on the Badia approximation. So there is a crossing point, and before the crossing point, the operant horizon is inside the event horizon. After the crossing point, it is outside. And also, operant horizon is if the collapsing is dominant, then it's a space-lag, and if evaporation is dominated, then it is time-lag. So you can also confirm the same behavior based on the Badia approximation. Of course, later I will show that the Badia approximation is too since Badia approximation is too naive. I will show more fundamental approaches to describe the dynamical black holes. So this is the generic recipe to draw the generic causal structures, global causal structures for any, almost all possible examples. So first we solve the integrated domain. So so this solve means that you solve by any way, analytic way, or in general in dynamical cases you cannot solve by analytic way. Therefore, by using computers or whatever, in principle you can solve all the local dynamics. So you solve the integrated domain, and let's say this you integrated in this diamond region, the white colored region. So the first step is to solve the integrated domain. And the second step is to draw the operant horizon. And you can decide the operant horizon from the local data. So by numerically, you obtain areal radius and you differentiate. And then if there is any point that RV equals 0, then you draw the operant horizons. And then also you need to find space-like singularity and future infinities if there exist. So there may be no future infinity, or there may be no space-like singularity, but you need to find whether it is or not. So this black thick curve is nothing but I conceptually draw the space-like singularity here. And then from the boundaries between infinities and singularities, for example, here there is a boundary between infinity and the singularity. So between infinity and singularities, we draw the causal boundaries backward in time. So now this blue dashed line is so-called the event horizon. By the same way, you can draw also the cosmological horizon or whatever, and also even Cauchy horizon too. So so the main point is that first, second, and third, all of them are about the local data. And from the local data and from the future information, you decide the global horizons later by the causal way. And finally, fifth, if there exists a point where we cannot decide, which is not a space-like singularity, then this may be the time-like singularity. Then we draw the null boundary forward in time, and this is called the Cauchy horizon. So in first, second, third step, all of them are the local things, and the other two topics are about the global horizons. So you first define local dynamics, and later you decide the location of the global horizons. This is the usual ethics of general recipes of the general relativity and decision of the causal space, causal structures. So as a very interesting application where, in genuine dynamical cases, all of the horizons are different for the charged black hole case. So this is so I will not discuss very details, but I will just show the conclusions about the charged black holes. So what is the charged black hole metric? And then the horizon, so in the static case, the horizon is located here, entropy is this, and Hawking temperature is this, and you can check this as maybe exercise. And in usual case, M must be greater than Q, satisfying with cosmic censorship. And as time goes on, M approaches to charge, M approaches to Q due to the Hawking radiation. However, if M approaches to Q, then Hawking temperature decreases. And now Hawking effect becomes weaker and weaker, but in that extreme limit, usually the Schwinger effect becomes now important because near the horizon, the electric field is strong. Therefore, this can emit the opposite charges. And due to the Schwinger effect, the black holes, or near extreme black holes, can be neutralized. So if you conceptually draw, then this is M direction, and this is the Q direction, and this diagonal line is Q equals M extreme surfaces. And if you start from this region, then this is naked singularity, and this is disallowed in many astrophysical contexts. So it's believed that you must start from this part, and due to the Hawking radiation, you will approach to the extreme black hole limit following the track B. At once you approach it to Q equals M curve, then you will mainly follow the this extreme limit because now the Schwinger effect is dominated. And there exists a critical limit that the Schwinger effect and Hawking effect are competitive. So along this competitive contour, this is the black dashed line, black dashed curve. So at once you reach this critical electric field, you will not follow the extreme limit, but you will follow this dashed curve. And eventually, the black hole size will be smaller and smaller, and even in in this limit now, the black hole size, charged black hole size is almost the same as the particle size. And then finally, it's quantum gravity regime, and black hole will be totally disappeared. So this is the usual life of the charged black holes. So then we may ask, what is the geometry of the gravitational collapse of the charged black holes, and what is the correct causal structure for the formation and evaporation of the charged black holes? That is a historical, very interesting question. So this is my quiz. So please answer which one is right. So I will show the answer candidates. The first one is Hawking Ellis in 1973, and Hawking and Ellis draw this way. So this is the star interior, and this is the outside static Ricen-Nordström solution. This is number one candidate. And in Birel and Davis' book in 1982, they draw the star interior here, and this is the causal structure of the Ricen-Nordström spacetime. So Birel and Davis draw by this way. And in the book of the famous general relativity, in Wild's book, they draw the star interior identified by this way. So compared to this one, they in Birel Davis draw this way, but in Wild, in the book of Wild, they draw this way. This was the star interior, or surface of the shell. This is number 3, and this is number 4. In 1998, Parikh and Wilczek drew this way. So now, this time-like singularity is even naked to future infinity. So based on the Vadia approximation, Parikh and Wilczek draw the entire space-time by this way. So from number 1, 2, 3, 4, from number 1, number 2, number 3, and number 4, what is the true answer? What do you think about this? And so if we are face in face, then maybe we can interact more. But unfortunately, I must say the answer, and the answer is that all of them are wrong. From 1, 2, 3, 4, all of them are wrong, because inside the charged black hole, the geometry is no more the Ricen-Nordström, because the inner horizon is unstable, and infinite blue shift happens. Therefore, at once you include such a blue shift, then you cannot rely on such a static solution for the inside. So this effect is known by the mass inflation, and due to mass inflation, there appears a space-like singularity inside the black hole. So space-like singularity appears, and if you go along the null direction, then there appears some null curvature singularities. So the causal structure might be something like this. This was proposed by Bonanno, Druce, Israel Musink in 1994, and this can be confirmed by numerical simulations. So as in my knowledge, the first successful numerical simulations are done by Hode and Piran in 1998. And I myself also reproduced them from my desktop computers, so in 2010. So the correct dynamical causal structure of the charged black holes look like this. So there appears space-like singularity and null inner Cauchy horizon, but inner Cauchy horizon is not regular. Curvature diverges at this null inner Cauchy horizon, and the apparent horizon is located inside the event horizon. So apparent horizon is entirely inside the event horizon because in this geometry we consider the no Hawking radiation. So I will not. I didn't say yet, but if you include the semi-classical energy momentum tensor to the charged black holes, then you will see some more modified space-time, and the real, maybe, I mean, more realistic dynamical charged black holes. So causal structure should have this kind of form. This is the main conclusion of my paper in several years ago, and I think this is the most reasonable and correct causal structure for genuinely dynamical charged black holes. Anyway, this was also my advertisement, and there are some further on charged black holes. So if a dilaton field, string-inspired fields are coupled to charge, then there may or may not Cauchy horizon and so on. So there are really from the string-inspired terms, they're indeed really fruitful and diverse behaviors of the gravitational collapsing black holes. So maybe my colleagues and friends wrote many papers about this. So up to now, I demonstrated by using the Schwarzschild black holes and charged black holes. For the Schwarzschild black hole case, maybe the causal structure is not that different from our intuitive pictures, but in the charged black hole case, if you don't really compute the interior structures, then the entire understanding might be very different, and even you can result a very wrong result. Therefore, the realistic computations and correct computations are very important to see the dynamical black holes. So then now we can move to.
Can I ask a question?
Yeah.
Well, I mean, can you explain again this instability of inner horizon and the formation of space-like singularities?
Okay. So if we naively see the Lyson-Nordstrom black hole, then there are two horizons. So in the outer horizon, usually we know very well that there is a redshift of the all modes. And then this means that mathematically in the inner horizon, inner Cauchy horizon, there must be the infinite blue shift. So at once there is an infinite blue shift, then we cannot trust the Lyson-Nordstrom geometry at all, because the back reaction is very serious. And so this was observed by Simpson and Penrose in several decades ago. And in terms of more local analysis, Israel and Pusan said the mass inflation. So by mass inflation, what we mean is that near the inner horizon, local mass parameter or local curvature quantities must exponentially increases as one approaches to the inner horizon. So this means that as you approach it to the inner horizon, curvature quantities, all curvature quantities must exponentially increases. This is the physical effects of the infinite blue shift. So infinite blue shift effect means the infinite blow. I mean the curvature blowing up to the beyond the Planck scale. So at the center region, there is a space-like singularity, and between the singularity and event horizon, there appears the null horizon. And then the question is, how can we justify this? So since we cannot rely on any analytic solutions for the interior structures, the only justification comes from the numerical computations. So in order to justify this space-time structure, you need to prepare the numerical data and introduce the gravitational collapse, and should see the result.
Okay, thanks. Thanks a lot.
Okay, so I hope this might be the answer. Okay, so now we go to the Hawking radiation issue. Then how can you justify quantum effects on a semi-critical background? So of course, using the Badia approximation, you may draw some causal structures, but as you could see the case of Parikh and Wilczek's paper, if you only rely on Badia approximation, then you can obtain a very wrong result. Therefore, we have to go in a right way. That is following the quantum field theory in curved space-time. And the most important two references are the book of Peter and Davis in 1982 and Davis-Furling-Unruh paper in 1976. So maybe I think you may have this book, or maybe you might see this book in some place. This is very famous paper in this field, quantum fields in curved space. So of course, this is a very difficult topic, and I cannot say everything. But let me just historically summarize about this topic. So we want to solve the equation, something like this. So I regard the metric as a classical quantity, but I want to include some quantum corrections to the energy momentum tensor. So then this means that we need to evaluate the expectation value of the energy momentum tensor. And then how can you compute the energy momentum tensor, expectation value of the energy momentum tensor? And the key point is from the two-point correlation function. So first you compute the two-point correlation function in the metric background, and by introducing several complicated derivations, you obtain more complicated form of the energy momentum tensor. This is a basic strategy. However, this is very complicated because in the curved spacetime, this two-point correlation function in general diverges, very simply diverges. So in order to resolve these divergence problems, we need the renormalization techniques to compute the regular two-point correlation functions. However, then how can we regularize the infinite quantities? That is really a problem. And if you regularize by a wrong way, then you will obtain definitely a wrong result. So Davis and his colleagues in 1970s found a way that if you introduce the two-point, if you introduce the point splitting method, and then you can renormalize all the things by keeping all the constant relations. So by point splitting method, the intuitive meaning is that in order to evaluate the two-point correlation function, you consider two different points, x and x prime. And if you compute x and x prime and expectation value, then it is non-divergent quantity. And if you consider the limit of x approaches to x prime, then there appears this kind of term, constant over x minus x prime, which is divergent. However, if you regard this as somehow the 1 over epsilon term as a divergent term, and you can introduce the counter term to cancel this, then eventually you will see the finite results. Of course, in mathematical details, it's very complicated. So if you are more interested in, then please see these references. And indeed, it's quite complicated, but the intuitive step is that you introduce the point splitting method and separate the divergent part. And eventually you cut this one. Then you can renormalize the two-point correlation function. And then by using this two-point correlation function, we obtain the energy momentum tensor by introducing many different complicated differentiations. For example, this is a very important paper introduced by Howard and Candelas in 1984. And in my knowledge, this is the most, almost the most, generic form of the renormalized energy momentum tensor. So the energy momentum tensor can have this kind of form, but this term can be obtained by differentiating this function g. So g is differentiated by complicated ways. Then what is g? And g is the two-point correlation function with two different points. So you obtain some very complicated differentials of two-point correlation function and consider the limit of x prime goes to x. And then by subtracting the divergent terms, you will obtain the finite renormalized energy momentum tensor. And this is the result of Howard and Candelas in 1984. However, I think this is really complicated. So I never tried to solve it. And one alternative approach was introduced by Don Page in 1982. In this case, Don Page approximately described the two-point correlation function by this way, but the principle was the Euclidean path integral approach. So based on the Euclidean propagator and Gaussian approximation, he could rederive the renormalized energy momentum tensor. And Don Page's result was not the same as Howard Candelas, but approximately they were same. And for some cases, Don Page's result was simple because it was the approximation. So in conclusion, there are several approaches to obtain the renormalized energy momentum tensor, and there are already some formulas, but all of them are extremely complicated. So in my knowledge, they are not very practical to describe the dynamical black holes. So what I will move is more simpler examples in two-dimensional case. This is the famous Davis-Fulling-Unruh formula. The energy momentum tensor near an evaporating black hole, but it is limited by the general two-dimensional space-time. Then in this two-dimensional space-time, the result is very simple. The metric is very simple. It only depends on this one function, and then you can obtain the renormalized energy momentum tensor by this way. One thing I omitted is some boundary terms of this energy momentum tensor. So there appears, and so if you read carefully about the Davis-Fulling-Unruh paper, then there are terms not only this, but also some additional terms. Then the additional terms only decides the boundary effect. And indeed, such a boundary effect is very important to derive the evaporation. So that is related to the choice of the quantum state, and it's named by either Bourel state and Unruh state and hot rocking state. And then Unruh state describes the evaporating black holes, and hot rocking state describes the eternal black holes. So there is an incoming and outgoing flux at the same time. So the black hole must be eternal. So I omit in this lecture, but there are some details in some additional boundary terms, but the local quantities are decided by this simple energy momentum tensor formula. So n list for the two-dimensional black hole cases, we can plug in this two-dimensional result and see the entire back reactions. So this is a common sense of general relativity. So in two-dimensional case, Einstein tensor vanishes. So definitely Einstein tensor vanishes. So there's no back reaction to the metric. However, for the dilaton black hole cases, there is a non-trivial, so non-minimal relations between metric and the matter field. And the dilaton is string-inspired models. So this means that in the dilaton black hole cases, even in the two-dimensional case, you can see the metric back reactions due to the evaporation of the, renormalized energy momentum tensor. This is the motivation of the CGHS model, Kalyan-Giddings-Armstrong in 1992. So CGHS is the original model in 1992. And in order to solve this two-dimensional model, maybe many people struggled, but CGHS is not solvable by analytic formula. Only it's numerically solvable. So several people introduced several terms to the model, and by imposing some global symmetries, one could obtain analytic formula for the solution. The famous one is the RST model, Russo-Susskind-Solagers model in 1992. This second model is very surprising because this can describe from the formation to the dynamical evaporation of the black by a compact and single formula, analytic formula. So a very simple formula. This includes everything about the formation and evaporation and entire things of the black holes. So let's go more details to this interesting topic. So this topic is known by the this title was of CGH was the evanescent black holes. So what do you mean by the evanescent? So evanescent means that this is a black hole but not a black hole. So when CGHS wrote first this paper, they vaguely thought that a black hole is formed, but due to the Hawking radiation, the singularity will not be formed. That was their original idea. So in CGHS model, they introduced this kind of model. So this is the dilaton, and this is the this term is the Ricci scala, and this is the Ricci scala and energy Ricci scala and kinetic term of the dilaton and cosmological constant term, and in addition, this is the scalar field to derive the Hawking radiation. And so this is the symmetry reduced action of the CGHS model. So in two-dimensional case, if there are many scalar fields contributing to Hawking radiation, then this action becomes a very good approximation because this can suppress all the higher order string corrections. So due to the non-minimal interaction between metric and dilaton, like some part like this, and there appears non-trivial dynamics even with the two-dimensional case, and maybe these are the equations of motion by choosing some gauges and so on. But mathematical details are not important at this point. Let's see the conclusion. So first, what they obtained is that by considering the null shell collapse, they could show the dynamical formation of a black hole in CGHS paper. However, if we turn on the Hawking radiation by introducing this term, then we can evaluate the dynamical evaporating process. And their conclusion was that as the shell collapses, Hawking radiation gives the back reaction, and eventually there is no formation of the black hole. So after adding DFU terms, Davis Spring unroot terms, CGHS misunderstood that there is no black hole formation due to the rapid evaporation. But I said this is misunderstood because if you compute this more carefully, then there must be a formation of the singularity. So in CGHS model, there is no analytic solution, but Pusan and Strominger in 1993, they simulated by them using the numerical technique. And then what they found is that even though we turn on the Hawking radiation, there is a formation of the singularity, and this is the apparent horizon, and there's endpoint, and you can draw the event horizon. So Pusan and Strominger numerically confirmed that indeed a black hole is formed even with semi-classical effect. So the original title was evanescent black hole, but black hole's CGH model is not evanescent. So this was confirmed by the numerical computations. But you may ask whether can there be any model that can be solvable by analytic formulas, and the answer is this model, Russo-Susskind-Dolatius model. So in this model, they modified a little bit of the original CGHS model. So this is the original CGHS action, and they included one more term here, something like this. So then you may ask what is the physical reason to introduce this, and indeed the physical motivation is, in my opinion, it is not very clear, but at once you add this term, then this space-time has the arbitrary global symmetry. So there's no strong motivation of such a global symmetry, but I may say, why not? Why not introduce this term? So maybe there's no problem. So at once you introduce this global symmetry, then this model can be analytically solvable. So, this is the function of a metric and dilaton field, and this is the solution. I forgot to mention details about what is omega and what is kappa. No, chi, but omega and chi are some dilaton and metric parameters. And then this is the solution. Not only including gravitational collapse, but also including the evaporation. So this solution includes the formation and evaporation of a black hole at the same time. And this formula is very simple. You can write just in one single line, but this includes everything about the formation and evaporation process of the entire space-time within the one loop order corrections. So in this sense, it is exactly solvable, and it is really interesting and surprising result. So by interpreting this RST model, you can draw the causal structure once again. So there are pros and cons with this global symmetry, and I will discuss later. So again, this is the same causal structures of the RST model. But I didn't copy this from RST paper, but I copied it from my paper in 2013. So again, there is a space-like singularity and apparent horizon, and they meet in a finite time, and there appears the event horizon here. So again, we obtain from the RST model, we obtain the same causal structure to the CGHS model. So in this sense, RST and CGHS both confirmed that indeed, even though we dynamically include the semi-critical effects, there must be a formation of the singularity. Okay, so this is the causal structure of the RST model, and one negative point is that so the horizon and singularity crosses even beyond the end point of the evaporation in the RST model. So in Hawking and Stewart in 1993, they conjectured and they thought that if singularity and apparent horizon approaches, and then eventually they will form Thunderbolt singularity. So the name is very surprising, but Thunderbolt means a singularity that spreads out to infinity on a space-like or null path. So originally, RST model seemed to say that there is a Thunderbolt-like singularity. However, it was not very clear whether the CGHS model still have the Thunderbolt problem or not. And the answer comes from again the numerical computations. In 2011, Ashteka, Pretorius, and Ramazanoglu. So Ashteka is an expert in GR, and Pretorius is very expert in numerical relativity. So they wrote the paper and they evaluated details of the CGHS model. And what they concluded is that as the black hole evaporates, the endpoint seems to be a remnant state. I mean, the black hole decreases the size and approaches a constant and non-vanishing asymptotic mass. So this recent numerical computations indicate that there is a formation of the remnant rather than the Thunderbird singularity or naked singularity. So maybe in CGHS case, no formation of Thunderbird. So probably that is the price to introduce such global symmetry in RST model. So in RST model, there is a Thunderbird singularity, but in CGHS model, there is no formation of the Thunderbird, and indeed it results the stable remnant. So based on this simulation, I saw the paper by Almeri and Sully in several years ago. And in this paper, they said that in 2 dimensions, in CGSS model, it eventually approaches to a long-lived remnant. So formation of a remnant, and this is they said that this is sufficient to explain all the informations in 2 dimensions. But I'm not sure whether, so I didn't check the very details. So I'm not sure. And there is such an assertion about the 2-dimensional CGHS model, but we need to recast whether their assertions are really true or not. Okay. So due to the time limitation, I need to very briefly review about the 4-dimensional case. So up to now, it's limited by 2 dimensions, but how can you extend to 4-dimensional case? And maybe we can do it. So in my knowledge, the first 4-dimensional application of this S-wave approximation was done by IR and Pusan in 1997, and I myself also did the same thing. So this is the paper of IR and Pusan in 1997. And what they did is to apply the S-wave approximation. This is a 2-dimensional result, and we divide by 4 pi r square. Then this is a crude approximation, but still within the spherical symmetry case, this may be a good approximation. And again, in this review article, I summarized some result of the evaporating black holes. And even in 4-dimensional case, you can see the change of the from space-like to time-like change of the apparent horizon. So you can numerically confirm the space-like to time-like change of the apparent horizon in 4-dimensional simulations. And also you can see the back reaction to the charged black holes. And you can apply the same technique for lower dimensional black holes, 3-dimensional black holes in ADS background, which is related to the BTG black holes. But this is about the dynamical formation and evaporations of the BTG black hole structures. So these are just the numerical details. And what I want to say is that you can compute even 4-dimensional case. I have several comments about the physics. So then what is going on in terms of the semi-classical physics? So the meaning of semi-classicalness, so maybe in terms of English, this is a very awful shape, but let me say, what is the meaning of the semi-classicalness? So we consider the following 2 quantum fluctuations. So first quantum fluctuation is here, and the other is here, and indeed it is superposed. And for each fluctuations, what you will see the back reaction. So this pink color is the metric back reactions. So usually in the semi-classical limit, metric back reactions are assumed to be very small. Then what is the average value? So because the expectation value means that it's averaging out all the contributions. So if you average this and these fluctuations, then the result will look like this. Some way between this fluctuation and that fluctuation. So if we consider the expectation value, then we will see the average, and this will be the average back reaction due to the average contribution of the energy momentum tensor. However, maybe you may feel that it is unfair because the quantum fluctuation is either left side or right side. But if you average out everything, then the contribution is only at the center. So you may say that this is unfair. So I think this is some remarkable point. So cosmological density perturbations are such an example. So if we average all the cosmological perturbations, quantum fluctuations, if we all average out, then the result is just 0. The average value is just the classical trajectories. However, in our universe, we see its individual fluctuations because after the horizon crossing, we select only one specific fluctuation. For example, left one or right one. And then we see the structure of the entire universe. Therefore, this may mean that when you average out all the quantum fluctuations, you need to be very careful. You cannot use this in any time, but you need to be very careful. So intuitively, two conditions are necessary. Of course, this is not mathematically rigorous statement, but intuitively we need two things. First one is that the back reaction must be very small. If back reaction is very big, then we must not average the quantum contributions. So this is one necessary condition. And the second condition is that these effects must be accumulated for a long time. So if you only naively compare this and that, then the average value is a center and it is unfair. However, if you add all 10 to 20 different kind of fluctuations, if you sum over all contributions, then the average value becomes very important. So if these quantum fluctuations are accumulated for a long time near the black hole geometry, then this semi-classical renormalized energy momentum tensor becomes a very physical result. So in the black hole evaporation case, we use the renormalized energy momentum tensor, and it is justifiable. But we need to understand the reason. There are two reasons. One is that back reaction is small, and the other is that we accumulatively integrate all the quantum fluctuations. That is the reason why the semi-classical description works in the black hole case. So maybe you may ask if there exists a quantum fluctuation that has a very low probability. So I mean, this has a very low probability, and this has very large back reactions. Then the expectation value may ignore such an important contribution because the back reaction is very big and the probability is very small. So if you average all the quantities, then maybe average point will be here. Then you can completely ignore the such contributions. However, this term may be very important in some aspects. For example, this is something like the lottery. So if we do the lottery all together, and try this, then what is the expectation value of the money? Probably you will say the expectation value of the money is 0. And if we try the game, then maybe nobody will get the money. I think so. However, it doesn't mean that there is a 0 probability. For example, if I've got the first prize of the lotto, then lottery, then I will get several $million, for example. I hope so. then I can divide some money to every students and professors in this classroom, and then the expectation value may increase a little bit. So what I'm saying is that if the probability is very small, then the expectation value may ignore it. But in the entire wave function of the space-time, such a highly suppressed histories may contribute very significantly if you see the entire structure of the wave function. So yeah, this is just my side comment. Finally, let me mention about this question. Will the semi-classical effect prevent the formation of a black hole or not? So usual misconception is something like this. So in terms of the coordinate time, if you fall into the black hole, how long does it take? So in terms of the coordinate time, it takes infinite time. So this means that it takes infinite coordinate time to cross the event horizon. So in terms of the outside observer, if this is the case, then in terms of the outside observer, no particle indeed crosses the event horizon. So maybe you may heard about this. You may hear about this story. So no particle indeed crosses the event horizon. Hence, every information is attached at the horizon, and due to the Hawking radiation, such an attached particles escapes from the black hole. Therefore, there is no genuine black hole formation, and black holes are only attached at the horizon and escapes from the black hole. This is the motivation of the membrane paradigm, and also related to the stretched horizon. And maybe later I will mention about the other motivation of the black hole complementarity. But today I will say that this is indeed a wrong concept, usual misconception of the general relativity for the dynamical processes. So even problematic interpretation was done by Kawai Masu Yokokura paper in KMY model. And in this model, what they obtained is that this kind of causal structure. So there was a null collapsing metal shell, and at the collapsing shell, they introduced the Hawking radiation. So as the shell collapses, shell emits the Hawking radiation, and it is of course right. It is okay. So this is so-called the pre-Hawking radiation. So Hawking radiation before the formation of the black hole. That is completely okay. But what their assertion is that such a back reaction is strong enough. So if a collapsing shell emits Hawking radiation, then they said that it completely evaporates before it forms an apparent horizon, nor singularity. Then from this causal structure, there is no way to lose the information. So this may be the resolution of the information loss paradox. So this was the motivation of the KMY model, and several general relativists also followed this kind of computations. And then in order to answer about the possibility, I myself and Pisin Chen, Bill Unru, and Jeong Woo will consider the case critically. And what we did is, so I mentioned CUWI model, and in this model, what we did is the dynamical description of the collapsing shell. So, so based on this formula, we can see the dynamics of the shell consistently. And this is the numerical result according to our computations. So what we did is that we didn't restrict the shell dynamics in the null direction, but we considered general cases from time-like null, including time-like null and space-like directions. So after very careful computations, one can confirm that the shell must move space-like direction at some point. This means that if the shell actively emits Hawking radiation, then there must be a back reaction to the shell, and at some point the shell must move from time-like to the space-like direction. So if any object moves from time-like to the space-like direction, then we call it the tachyonic object, and tachyonic object moves a causal way. So if any physical object moves a causal way, then we may say that it is completely wrong. So this conclusion is very unphysical. So in this paper, what we focused on is the to demonstrate the KMY model, and we have shown that indeed black hole must be formed, and their assumption was a little bit inconsistent in some point. And there might be some causal move of the shell if there is no formation of the black hole and so on. So about the infinite time issue, usually the coordinate singularity appears at the apparent horizon. So coordinate singularity appears the apparent horizon, but apparent horizon is different from the event horizon. So if we consider the back reaction carefully, then event horizon is different from the apparent horizon. So when you cross the event horizon, still the coordinate time is finite. therefore, this means that the outside observer will see that the inferring matter disappears within finite coordinate time. So an inferring matter can cross the event horizon within a finite coordinate time because the event horizon is not the coordinate singularity. The event horizon is not the apparent horizon. This is the way to escape the paradox of the black hole formation. Okay, so maybe this is one important application for the dynamical horizons. Okay, that's all today. Thank you very much.
Thank you for a very great lecture. Please feel free to ask any question for today's lecture. Let me ask one question about the CGHS model.
Yes.
So, is it like a? Is it possible to study this near singularity or singularity itself with this CGHS model?
Sure. I think you can see the dynamics near the singularity, but the problem is that in CGHS model, it is basically general relativity plus renormalized energy momentum tensor, which includes the H bar order. But near the singularity, you have to include the H bar square, H bar cube, and all higher order quantum corrections. But this is very difficult to deal.
So in the end, that near the really close to the singularity, one cannot believe this analysis. There must be more.
In that limit, we need quantum gravity.
I see. Okay. So here you also consider large n matter, or?
Right. So practically, we don't need a large n, but if we say about the large n, then this may mean that we neglect all higher order corrections. But if n is not infinite, then still there survives higher order corrections. So in the near the singularity, we cannot ignore them.
If there is a lot of matter, okay. Okay. Thank you. Any other question?
Excuse me. So
yes.
in the mass inflation,
yes.
So inner horizon is crucial.
Right.
But what about the outer horizon? Yeah. So actually, in the outer horizon, the particle can be UV shifted. Okay. So what is the difference between the inner and outer horizon?
So in the outer horizon, modes are red shifted, and in the inner horizon is blue shifted.
But I think that actually in the near horizon, the particle can be blue shifted actually. No? Blue shifted Tolman temperature can be red shifted at the asymptotic infinity.
Right. So I think what you mean is if you stay at a constant radius, then maybe of course there appears some factor that increases exponentially. However, here what I'm saying is about the evolution of modes. So I think if you consider the evolution of wavelengths, for example, then this doesn't stay a constant radius. So I think it's a little bit different.
So different role between the inner horizon and the outer horizon?
Right.
Different. So
right.
It's confusing. Okay. Thank you.
Okay, thank you.
Any other question? If not, let's thanks lecturer again.
Okay, thank you very much.